In this video lecture, we'll start introduction of a very important topic, slider crank mechanism. This we have already discussed in part in our earlier video lectures also. Now onwards, we will do detailed analysis of velocity, acceleration and forces in this mechanism. A slider crank mechanism is obtained by the concept of equivalent linkage in a 4-bar chain. So as we discussed earlier, a 4-bar chain, if one of the link is made infinity, length of the link is made infinity, then the rotary motion of this crank become almost like a horizontal motion. So this is replaced like this, and you get almost horizontal motion of this link and a rotary motion of the crank. And a revolute joint can be replaced by a prismatic joint. Prismatic joint means a sliding pair. So to move one step further, if you replace the rotary joint by a sliding pair here, this becomes a slider crank mechanism. Now, if you apply the Grashof condition to the sliding pair, you can get two varieties of the slider crank mechanism. So, if you recall our earlier discussion, the Grashof condition classifies the links, a mechanism, by the length of the links, ratio of length of the link. So we usually have the longest link, the shortest link, which is usually the crank, which is having complete rotation possible, and the other two links are called P and Q. So Grashof's condition is that L plus S must be less than P plus Q. So if you see our discussion at present, that a slider crank mechanism is a special case 4-bar linkage where the length of one of the links is infinity. So because of the infinity length, R being infinity, you get almost horizontal motion of this link, and by the concept of equivalent linkage, the rotary link, the rotary chain can be replaced by a prismatic or a sliding pair. So application of Grashof's condition to a sliding crank mechanism here would mean that we have to substitute Q is equal to infinity in this condition. So if Q is infinity, then the Grashof condition is always satisfied. In the case of a slider crank is always a Grashof mechanism. So this can form one objective question. So we should keep this in our mind for our knowledge. Okay, so in a Grashof mechanism, what are the different kind of categories are possible? So you can have a crank rocker. So this is the most versatile application of the sliding crank mechanism. You have a sliding pair here. This is the shortest link S, and if you recall our conditions of Grashof's different mechanisms, a crank rocker is obtained when link adjacent to the shortest link is fixed. So in this case, this crank is the shortest link and the link adjacent to that is fixed. So that's how you get a crank rocker arrangement. You can also fix this link and it will be a different inversion of the sliding crank mechanism. So we will have one crank at least here. Other category is a double crank mechanism which is obtained when the shortest link is fixed according to Grashoff's condition. So here you may fix the link as the shortest link is fixed to the ground. So you have this pivot point, and the longest link is not this is the part of the mechanism now. So you get a mechanism somewhat like this. So in this mechanism, if the shortest link is fixed, if the link which is fixed is the shortest among the all, complete rotation of both the slider and the cylinder inside which the slider is kept is possible. Double crank. So the shortest link is fixed here to get a double crank. Interestingly, there is also a crank rocker mechanism which looks quite similar. We will be covering the details as we move along the video lecture. So here, this is the shortest link. So, and the link adjacent to the shortest link is fixed. So this results in a crank rocker. So both of these look almost similar to each other, but here the shortest link is fixed, that is this one S, and here the shortest link adjacent to the shortest link is fixed, and this is the shortest link. So here you get a crank rocker. So just by application of Grashoff's condition, you can different kind of mechanism which are almost similar looking, but due to the ratio of length, they have different behavior. The third category, rocker. This, if you recall the Grashoff's condition, the rocker will come when link opposite to the shortest link is fixed. So I will illustrate one example here. In this case, we have made the connecting rod the shortest link, and we have made the crank long, maybe P or Q, P or L. Q is anyway infinity. So Q is the sliding pair. So Q is anyway infinity. The links opposite, so this is the shortest link. The link opposite to the shortest link is fixed. So in the 4-bar terminology, this will look like this: L, H, Q, and P, and Q is made infinity here. This P, which is the link opposite to the shortest link, is fixed, and it results in a rocker arrangement. So here this crank cannot have, this cannot be a crank, and this link cannot have a complete rotational motion. It can only have a rocking motion, and the sliding pair anyway has a rocking motion. This link opposite to the shortest is fixed. Now in practical mechanisms, the double crank and the rocker are hardly useful. The mechanism of paramount interest is the crank rocker mechanism. So from here onwards, we will take forward the crank rocker mechanism only, and we will see its various inversions. The crank rocker is simply referred as the sliding crank. So here you have one crank which has the complete rotation, and one sliding contact which is having the rocking motion. The piston is having the rocking motion. So if you are saying a mechanism is a sliding crank, that inherently means that it is a crank rocker mechanism, and it is a Grashoff mechanism where the link adjacent to the shortest link is fixed. So nomenclature of a single slider crank. Single slider crank is obtained by fixing one of the links and making it a sliding pair. So this is often the shortest link in the mechanism. When you are using the slider crank, then as we just discussed, this link needs to be shortest. So it is for the rotary crank. So this will be our crank. This is connecting rod. This will be the piston, this is a sliding element, and this is liner. So you saw that the slider crank mechanism was obtained by replacing one of the joint in a 4-bar mechanism by a sliding joint. What happens if you replace this link also by a sliding joint? Then this is called a double crank. So that's why I was using single slider crank just now. Here you have replaced only one rotary joint in a from a 4-bar chain, and if you replace two, it is called a double crank. So a double crank mechanism, I will draw one sketch here just to illustrate you how it can be formed. So you have pathways like this which are fixed to the ground. And you have the double piston arrangement inside. This is how the piston arrangement looks, and the both are connecting by the coupler link. So in this mechanism, when this piston moves downward, then this piston is moving inside. It comes to the central position, and then it keeps moving forward, and it goes here. When it is moving downwards now, this piston starts coming back. And then when it reaches its extreme position, this piston is in the center, and when it starts moving up, this piston is moved forward due to inertia, and when this piston reaches the central position of the mechanism, this piston reaches the extreme position. So likewise, you can see the movement. The animation of this movement of the double crank mechanism is freely available over the internet. So this is called double slider crank mechanism. So you have two sliders here, and this is the link which has the complete rotation. That's why a crank is also there. So I'll show you the various position of the double slider crank to make you visualize it better. So this is the position 1. When this moves forward and this moves like this. When it comes to its extreme position, in the center position, this comes at its extreme position. So this is the center, this is extreme. Both are connected like this. So this is having movement like this, this is still having movement like this. When it starts to move down from the center, then it becomes like this. So the second piston starts coming back now, and this piston is still moving down. When it reaches its extreme position, downward position, the second piston is in the center. So it's having almost zero velocity, this is having downward velocity. Both are, so this thing is having a forward velocity, this is having almost zero velocity because it has reached the extreme. Then next time step, it moves forward, and this starts coming back. So at this instant, it looks like this. This is moving forward, and this is coming down. So this kind of motion is formed 1, 2, 3, 4, 5, and it keeps repeating itself. So the double slider crank, we will study some inversions of the double slider crank also, one of the single slider crank also. When we will see the inversions, we will understand their physical application. Now we move to the topic of inversion of a single slider crank. The first inversion is obviously a reciprocating engine, or compressor, where a simple basic single slider crank is employed. So this is a sketch of that. You have a crank, you have a connecting rod, piston, liner. So in IC engine or reciprocating engines, this is used to transfer work from piston to crankshaft. In reciprocating engine, and reverse way in compressor. So a compressor is driven by a motor, so that is a rotary motion input, and it is converted, the rotary motion is converted into reciprocating motion of the piston. The thing, and you have two varieties of this first inversion. One variety, the axis of piston passes through the center of the crank. So this is called inline slider crank. And the other category is where the axis of motion of the piston is off center to the crank center. So there is a gap between both. So this is called offset slider crank. The motion of an inline slider crank mechanism, if you consider the motion of the piston depending on the motion of the crank, assuming constant speed of rotation of crank, motion of the piston is sinusoidal. So we will be showing in detail about this velocity relations between the velocity of the crank and the velocity of the piston. We will derive it, and in the offset mechanism it is not sinusoidal. It is some variation of the sinusoidal, like an additional factor will also come in picture. So this mechanism is not considered in much more detail. You just should know about it. What is the off-center slider crank? Because in the offset slider crank, depending on the offset, different kind of motions of the piston can be generated. So they are developed especially for special applications, and it cannot be generalized. And so from our syllabus point of view, we will do derivation of the inline slider crank, and the special applications of offset are reserved for further studies. Under the category of second inversion of sliding crank mechanism, we have the Whitworth quick return mechanism and the rotary engine. So we will consider the Whitworth mechanism first. So in the slider crank mechanism, I'll draw a diagram here. This is the crank, this is the connecting rod, this is the piston and liner. So in this configuration, the link adjacent to the crank is fixed. So this is a fixed link. In the bitward motion for second inversion of sliding crank, instead of fixing the link adjacent to the crank, we are fixing the crank itself. So in this configuration, if you fix the crank, let's say like this, and the connecting rod is going and connecting to the piston, and now the liner is also part of the mechanism, so it will form a link. So this is connected like this. So this becomes a link. This is not fixed, and the crank is fixed. So inversion means that in a mechanism or a kinematic chain, you are fixing different links and you are getting a different mechanism. So this forms a Whitworth quick return mechanism. Why the word quick return is coming? For that we will draw a separate sketch. So I'll draw this mechanism in a different scale now, different alignment. So this is our crank, which is fixed. And then you have the connecting rod, which is having a piston like this. The piston is contained inside a cylinder or a sliding link, and this sliding link is pivoted to this rotary joint. So in this mechanism, the crank rotates full 360-degree revolution. This is the rotating element now, and the cylinder assembly is having oscillatory motion. And the connecting rod is having full rotation. So this sketch is nothing but the same sketch that I have drawn here on the left hand side, but in different alignment. So how it forms a quick return motion? For that you have to consider the trajectory of the piston. The trajectory of the piston will be a circle. So I'll draw a simple schematic here of the trajectory of the piston. So the piston will be moving in circular fashion, a different angular rotation to the motion of the connecting rod. And now you consider the motion of the output, which is the cylinder. Motion of the output, the cylinder, it is pivoted about a link which is off center from the crank. So you draw a line tangent to this circle and tangent to the circle, two lines you will get. Tangent to the circle of motion of the piston, and these are the two extreme positions of the cylinder. So if you consider travel of the cylinder, you have an angular movement of say theta while returning. So this is a forward stroke. When the crank is moving from this position, say A, OA to B, OA to OB, the angular motion of crank results in forward motion of the cylinder. So this is the forward motion OA to OB. So the angle for that is 2 pi minus theta in radians, and for return while coming back, the motion is from OB to OA, that is return motion of the cylinder. So if you come back to it, So from OA to OB it will go to forward position, and from this angle OB to OA it will come back in return. So as you can see from this figure that theta is less than 180 degree. So the angle for forward motion, angular displacement for forward motion is more compared to the angular motion of the return path. So for a constant angular velocity omega, the time taken for forward motion will be 2 pi minus theta divided by omega. So omega is in radian per second. So 2 pi minus theta, radian divided by radian per second, it will give you seconds. Forward time is 2 pi minus theta by omega, and return time is theta minus omega. So as you can see from this picture that theta is less than 180 degree. So 2 pi minus theta is greater than theta. That's why t forward is greater than t return, because theta is in numerator. So this quantity is small, this quantity is large. That's why t forward is greater than t return. So the time taken for forward motion is greater than time taken for the return motion. That's why this mechanism is called a quick return mechanism. The quantity t forward by t return is sometimes called quick return ratio. So time taken to move in the forward direction divided by time taken in the reverse direction. So this is greater than 1 because Tf is greater than Tr, and it is equal to 2 pi minus theta by theta. So if theta is less than pi, then this will be obviously greater than 1. The application of this mechanism is in some cutting tools where you want the reverse motion to be rapid. Return motion should be rapid and the forward motion should be slow. So you have some tool which is operating on some job that goes forward, like a hacksaw. So in a hacksaw cutter in your laboratory or workshop, you can see this hacksaw cutter where the forward motion is slow. The hacksaw is cutting the job. This is a hacksaw. This is a job. So hacksaw is cutting the job. So forward motion takes time. It's slow, and it lifts up and comes back very quickly. So such kind of cases you use a quick return mechanism. Another category, another example in the second inversion is rotary engine. So we draw the sketch here of the second inversion. The crank is fixed. You have a cylinder like this, the piston inside that, and the piston is connected by this. This is the second inversion. So a rotary engine, this is used, like the rotary engine is used in aircrafts in the period of 19th century. Now we will hardly find these engines in operation. They can be still viewed in workshops of mechanical engineering. So you have a radial cylinder arrangement. These are all cylinders, cylinder blocks, and inside each cylinder you have a piston. So piston, and they are connected to the crankshaft. So this is the center of the crank. So crank center. This is the crankshaft, and this is the connecting rod. So in this case, in the case of rotary engine, what happens is that you are fixing the crank. So fixing the crank and the cylinder block assembly rotates. So in normal IC engine, you have the crank rotating and the piston moving up and down. Here also the piston is having translational motion up and down, but here the full cylinder block is rotating at a constant angular speed. This configuration was used to save space in aircraft engines. So this is a center, and due to this eccentricity, all of them are connected. All of pistons are connected to the connecting rod by this eccentric point. To this eccentricity, the piston moves up and down. So same kind of motion, but here the cylinder block is rotating. This is another example of the second inversion of a slider crank, where you have this cylinder block. This is something similar to the cylinder block, and this is your connecting rod. Piston still moves in a oscillating fashion, and the crank is fixed.